Hello, this is Solutions to Homework 2. Let me begin with problem 1. Problem 1 asks us to plot the motion of an object with equation x equal to vt. So x equal to vt. And in part A, in particular, we have v is given to be 3 meters per second. Recall the this is a linear plot. As time increases, x also increases. First of all, at time t equal to 0, x is equal to 0. And for a very large time, x is going to be positive. So let's clarify that. So that's your x. That is time. And it surely passes through x equal to 0. So it's x as a function of time, and that's t. So it passes through x equal to 0. And for large time, let's say a positive large time, since the velocity is positive, it'll be somewhere here. The slope is 3 meters per second. Since we don't have a scale really to measure with respect to what, if t was in seconds, then we know the tangent of what angle is 3, tangent of 45 degrees is 1, so it should be more than 45 degrees. So we can expect this, oops, zero. So that's a straight line, and I stretch this out. So that's your motion x equal to vt. What's the example of a motion that has this particular scenario? Let's think of x-axis to represent a, a main street in a town, and we could be having a point A here and point B here. And you're going from point A to point B, but it's not that you're starting from rest at point A, you're simply crossing the street. So it is, you're maintaining constant speed while going through. So A could be uh, a house 1 and B is house 2, and it's connected by a straight line, and you're crossing point A and point B with constant velocity 3 meters per second. And since B is at a larger distance in the direction of x, you reach B at a later stage. How will it be different if V is equal to minus 3 seconds? So let's consider what happens if V is equal to minus 3.0 meters per second, assuming that t is in seconds again. At t equal to 0, again we have x equal to 0. So again, let's consider a plot here. And again, we have, since it passes through x equal to 0, so with this surely it's a point in here. But for large time t, so let's say this is t and that's your x for large positive time t, because v is negative minus 3, so this is going to be a negative number, so it's somewhere in the fourth quadrant. And for large negative time, this becomes a positive quantity, so it's pretty much similar to what we had earlier, but now the slope is in the opposite direction. And time is going forward in the forward direction. So if we again have, if we say we are on the same street and we have point B here, point A here, since time is evolving forward, so this is a motion which is going from point B to point A. So here the earlier the motion was from point A to point B. So motion is in the first case A to B in the graph that is plotted. And here the motion is again uniform velocity. They don't stop at point A or at point B. It crosses point B first and then crosses point A, where A is at the origin, let's say. So that's broadly speaking what the plots represent. There's one more part to this question. What is the acceleration of the object for these cases? So C acceleration will be a second derivative of position. So first let's say dx by dt. So that's equal to simply v, and second derivative is 0. So acceleration in both cases is equal to 0. and and let me pause for a moment before I start problem 2. Let me start problem 2 in the homework. So it is getting recorded, yes. Problem 2 in the homework asks us to plot. There are about 6 parts to this with various initial conditions. So let's start with the scenario x is equal to 0t plus half at squared. So that's 0 plus half times 2t squared. 2 there should have units of meters per second square, but to avoid clutter, let me avoid writing that. So what I have here is x is equal to t squared. I can immediately think of velocity. Velocity will be the derivative of this. So that's 2 times t. And acceleration is equal to uh, a derivative of velocity. So that's just 2. And since we had 2 sig digits there, so this should be 2.0. At this point, I can say this is meters per second square. I can also clearly uh, argue what is position at time t equal to 0. So that's equal to 0 itself. Velocity at time t is equal to 0. That's also 0. And acceleration at time t equal to 0, that actually remains constant. It is time independent of time. Based on this, we should be able to do a few, at least characteristics of the plot we should be able to recognize. So let's have a plot here. So that's your axis, and let's say that's time t, and that's x as a function of time. We are given that position at time t equal to 0 is 0, so the path of the particle surely crosses the origin here. Velocity at time t equal to 0, uh, while it is at the origin, its velocity is 0. That means the slope of the path when it is crossing there is actually 0. So it goes horizontally. That's what it means. So there's a tangent to that at that point is 0. And the acceleration is plus 2.0. So that means to say that it is going to increase in the x direction. So its velocity is supposed to increase in the x direction. That means it will go upward. It is also possible to see that for large t, what happens to position x for large positive time t, x is t squared. So that means it has to go somewhere here, right? For large x, it should be going in that direction. So it starts from here, goes there. It is a tangent in here. So it is expected to go this way. And if we can plot it on the other side also for negative time, for large negative time t, again it goes positive. So that's the shape of a parabola. So the motion is in this manner. This is a parabola that cuts the x-axis at exactly at one point, and so we know it is at the origin. So we pretty much know all the characteristic of this curve at this point. If we were actually having it cut at 2 points, then the question arises as to where does it cut. But at this in this manner, we don't have to worry about that. In part B, we have pretty much the same equation, except this is having acceleration to be minus, so that's minus 1 by 2 t square. That leads to position function as a function of time to be negative t square. Velocity comes out to be minus 2t, and acceleration comes out to be minus 2.0. If you want, this also should be 2.0 here. Again, at time t equal to 0, the position is 0. Velocity at time t equal to 0 is now minus 2.0. And just to put in the units there, let's meters per second. And acceleration, so this is also meters per second square. Acceleration at t equal to 0 is minus 2.0 meters per second square. Oops, that's a mistake. So this at velocity at time t equal to 0 is 0. Eraser. So that's 0, and this is meters per second square. Again, let's see, how do we plot this? This is pretty close to whatever we did earlier. So that's your axis, time t, and position x. Again, at t equal to 0, the position passes through the origin. So that's x equal to 0 is surely part of the path. Velocity is still 0. So at t equal to 0, velocity is 0. That means its slope at this point is again horizontal. Acceleration is minus 2.0. That seems to suggest that this is going to, this parabola is going to face downwards. But another way of seeing that is that go back to the position function. And for large t, for very large t, it is the highest power that will dominate. So it is t square, which is a positive quantity, but with a negative sign. This is going to go this way. And for very large negative time, again, it is squared. So it again still goes negative this way. Right? These sort of captures the shape of the curve. So it is expected to go this way. It is supposed to have a maximum there and come down. One might wonder, why can't I go up here, then come down, and then go here and come this way? But then that has to be a higher order polynomial, quadratic. A polynomial degree 2 can cross the x-axis at the most only 2 times. So that kind of constrains this. And once we have this, the only characteristic of this curve is that it actually has a maxima at the origin, and nothing else needs to be described after that. Let's go to part C of this problem. So it's homework 2, problem 2. And let's say this is part C. And our function, the position as a function of time now, is having velocity is equal to 1.0 times t, and acceleration is plus 2.0. So that's plus half times 2.0 t squared. which is 1.0 t plus this is 1.0 again if you want t square. That's a function, a position as a function of time. Immediately, let's take some derivatives. So velocity is the derivative of this quantity. So that's 1.0 plus 2.0 t. And acceleration as a function of time, take the derivative again. So this is 2.0 meters per second square. All right. What's the position as at time t equal to 0? So that's equal to 0 itself. So that means it goes through the origin. Velocity at time t equal to 0. That's no more 0 like we had earlier. This time it is 1.0 and bring the units back. So it's 1.0 meters per second. And acceleration remains a constant. So even at time t equal to 0, that's 2.0 meters per second square. So what are the characteristic that's comes in? So let's have the axis drawn. So that's your axis. And again, let's look at this. It at time t equal to 0, this is passing through the origin. So that's part of the path of the curve. And that's your x and time. And now at time t equal to 0, there is a velocity of positive velocity. That means the slope of this curve at this point is a positive quantity. So that's somewhere the path of the curve crosses the origin in that form. And next we are given that or we can look at the position and ask for very large time. Remember, for very large time, the highest order of the polynomial is what dominates, because if you have a number like 10, a squared number 10 will be 100 and t will be just 10. Usually for very large time, you can keep going. The coefficients does not matter in that case, because you can always pick a higher time than the coefficients themselves. So for a very large time, it is the quadratic term that dominates. And if t is positive, then x is positive. So it actually seems to go this way. So that's your place. For negative time, again, for negative large time, again, quadratic term dominates. Again, it is positive because it is a squared quantity. And that means to suggest that this is going somewhere here like this. And we also know that a polynomial of degree 2 can at the most, it may not cross at all, but at the most it can cross 2 times. It's already crossing the x-axis. By x-axis, I mean the horizontal time axis here once. So, and we know that it has to go up on the left. So that means it has to come back. So the plot seems to be like this, and it's a parabola. So it's like this. It should be smoother than that and symmetric on both sides. And the moment you say that's your plot, we have to specify the characteristics of this. We should ask, what is this? That's t equal to 0, sure. But what is this point? So that's a characteristic of the plot. Where does it cross? And further, we should be able to convey at what point does this turn, right? Those are the characteristics of the plots. How do you find when does it plot the x-axis? Just set x equal to 0. So setting x equal to 0, we learn that 1.0 t plus 1.0 t square has to be equal to 0, because position was given by that. Let's stop writing 1.0. So we have t times 1 plus t, right? That's equal to 0, because first one is t and t square. There's just two solutions at t equal to 0. This, if t was equal to 0, that equals 0, and it is also equal to 0 when t is equal to minus 1. And that's your second solution. So that's 1 minus 1.0 seconds. So we know that now. So this is This is actually minus 1.0 seconds. That's 0 seconds minus 1.0. So somewhere here is plus 1.0 seconds. So that gives us a scale. And we also know that the velocity goes to zero exactly when it reaches the minima point here, right? Because the tangent down here is 0. So at what time does that happen? So we just have to set velocity equal to 0 there because the slope is horizontal there. So now we set velocity equal to 0, which means we are setting 1.0 plus 2.0 t to be equal to 0. That implies that t is equal to minus 1 by 2, which is 0.5 seconds, which makes sense. If this was symmetric, this should be exactly in between. So that's 0.5 seconds. Once we have that to be 0.5 seconds, we can ask what is the value of this position at that point, and that will describe the curve completely. So at t equal to 0.5 seconds, what is position? We just have to find that. So x at t equal to t equal to minus 0.5 will be 1.0 times minus 0.5 plus 1.0 times minus 0.5 squared. So that's minus half. The first term is minus half, and the second term is plus 1 by 4. And minus half plus 1 by 4 is minus 1 by 4, which is minus 0.25 meters. Right, if we put in all the units, so that's equal to minus 0.25 meters. So this is minus 0.25 meters. That describes all the characteristics of the curve, and it's a parabola, of course. Its acceleration is plus 2. So that's part C. Part D is very similar, except that 2 is it is minus 2 as opposed. Part D is velocity remains the same, so it's 1.0 t minus uh, 1 by 2 times 2.0 t squared. That's 1.0 t with 1.0 having meters per second and 2.0 having meters per second squared. That's this again, this will become 1.0 times t squared. Very similar to that, except for that negative sign, and that changes the characteristic of the curve. So velocity now, take the derivative, it's minus 2.0 t, and acceleration is minus 2.0 meters per second squared. What's the position at x equal to 0? That's 0 again, so it passes through the origin. Velocity at time t equal to 0 is 1.0 meters per second. It's positive still. And acceleration at time t equal to 0, it remains a constant all through, so it is minus 2.0 meters per second squared. Slight differences from the earlier example. So let's see what are the differences. So let's see our plot again, or the axis for the plot we prepare. And let's label them as time t, and y is the exact or the position axis on the vertical axis. It the at time t equal to 0, the position is 0, so it passes through the origin for sure, and the velocity still is positive, so that means the slope is positive. So that tells us that this is down here again. But we expect this to be slightly different because it has a negative acceleration. So how is it different? Let's again look at what happens to the position for very large time t. When t is large, it is dominated by the highest highest power in the polynomial. And if t is positive, t square is positive, but the -1 makes it a negative. So it seems like for large t, you go somewhere here and argue the same thing for negative t. You say that it goes negative direction. Parabola has to cut the axis at the most two times, either two or zero number of times. That's the possibilities. So it seems clear that this is a parabola like this. And like earlier, so this is now clearly different, but the characteristics are, again, we should find where does it cut on the x-axis, where does it become a maximum, and wherever it is maximum, what is at what position, at what point in along that line x-axis does it become a maximum. And again, we set x equal to 0 gives the information about where it cuts the axis. So that means t minus t square is equal to 0. So that means that t is equal to 0 and t is equal to 1.0 seconds plus 1.0 seconds this time. So that's 1.0 seconds. That point is 1.0 and this is of course 0. Where does it become a maximum? For that we set velocity equal to 0 because right at that point the slope is equal to 0. Since the slope is 0, velocity is 0, so that means 1.0 minus 2.0, t has to be equal to 0. That implies that t is equal to 1 over 2, so that's plus 0.5 seconds. 1 by 2 is 0.5. So that way we learn that this point where the curve reaches a maximum is 0.5 seconds because the velocity is 0 there. Once we know that time, we can ask what is the position at that particular time, and that will be the point described here. So evaluate the position at time t equal to 0.5. So that's 1.0 times 0.5. That's your position, first term in the position function, and minus 1.0 times 0.5 squared. That's half. The first term is a half, and the second term is uh, is 1/4. So 1 by 2 minus 1 by 4, 1/4 is a 1/4 itself. So that's 0.25. Very similar to the earlier problem, except earlier we had a positive. So this is, or earlier we had a negative, and now we're getting a positive number. And this is in the units of meters because that describes position. So that gives us a clear picture of how we capture the graph. Even if, of course, one can give this into software these days and it plots. But then we should also have a clear way of visualizing or capturing these numbers just from the function itself. Uh, Similar things can be done for part E and part F since the numbers remain the same. So all these characteristics remain roughly the same. And let me quickly do that. Part E, so homework 2, problem 2. And this is part E. So it's x is equal to minus 1.0 t plus 2 point plus actually 1 by 2 times 2.0 t squared. So x is minus 1.0 t plus 1.0 t squared. Velocity is minus 1.0 plus 2.0 t squared, and acceleration is plus 2.0 meters per second squared. Before we plot, let's also point out that x is equal to, at time t equal to 0, position is 0. Velocity at time t is equal to 0 is minus 1.0 meters per second. And acceleration at time t equal to 0, which remains a constant anyway all through, is 2.0 meters per second square. That's your axis. We have time t here, x in the vertical, x for the vertical axis. And the only difference here now is that the velocity is negative at time t equal to 0. It is position is 0 itself, but velocity is negative. That means its slope is this way. The rest of the arguments remain exactly the same. So we argue that this actually goes like this. And since the numbers are exactly the same, all the process in the earlier parts repeat. To get this position, we again set x equal to 0, and it comes out exactly to be 1.0 seconds like earlier. This will again come out to be 0.5 seconds, and this will again be 0.25 meters. The process for that remains exactly uh, the same because the numbers are pretty much the same. The difference here from part C is that this is now shifted to the right. So without doing the details there, I go to part F because it is reasonably the same idea. Here now, x is minus 1.0 t, and acceleration is minus again. So it's both velocity and acceleration is negative, and simply because acceleration is negative doesn't mean that it is slowing down. I think it is only when the velocity and acceleration are in opposite direction then it means it is slowing down. So this is speeding up because velocity is in the same direction as the acceleration. So x is equal to minus 1.0 t minus 1.0 t squared. Velocity again is minus 1.0, but this time it is minus 2.0 compared to earlier, and this is minus 2.0 meters per second square. At time t equal to 0, it helps to know that we know that we can, it helps in plotting. And velocity at time t equal to 0 is minus 1.0 meters per second, and acceleration at time t equal to 0 is minus 2.0 meters per second squared. Again, have our axis. At least I will draw the plot and not do the complete detailed calculations there. And it again passes through the origin. So it's t, that's your x. It still passes through the origin, but this time with a negative slope. And at a large t, using the position graph, we know that it will be negative. So it seems like we will have negative here and on the side. So completing the characteristic, it seems like this will be like this. It will be a plot. Again, the numbers remains the same since at what position will it be 0? It is clear that it is t and t squared. So this will be minus 1.0 seconds. The point where it becomes a maximum will be minus 0.5 seconds. This is of course 0. And where at what's the position when the velocity comes out to be 0, comes out to plus 0.25 meters. Again, that those points characterize this curve. Good. With this, hopefully there's a reasonable picture of how to visualize something going with constant acceleration using plots, or in general, if you have a function of time, how do you read out the properties of the motion is a field for. Let me pause at this moment and I'll come back. this is problem 3 in homework 2. Here we are given the position as a no, we're given the velocity as a function of time, and we're not given the specific numbers, so we have variables. So this is v naught plus a naught t plus half v naught t squared, right? So that's the information given. Part A asks us to calculate what is the particle's acceleration as a function of time. Acceleration is derivative of velocity with respect to time. When we take the derivative, v naught, a naught, and b naught are not explicit functions of time, so that's 0. The second term is linear in time, so that's a naught, plus the third term is quadratic, so it is 2t. So 2 cancels out, and we have b naught times t. So that's equal to a naught plus b naught times t. So that's good. That's your acceleration. In part B, we are asked to determine the particle's rate of change of acceleration as a function of time. That means we have to take the derivative of acceleration again. So this is derivative of acceleration with respect to time, rate of change of acceleration with respect to time. The derivative again, a naught does not contribute, so that's 0 plus b naught. That's equal to b naught itself. That's your rate of change of acceleration. In part C, we are asked, given the particle starts from rest at time t equal to 0, determine the velocity of the particle when the instantaneous acceleration of the particle is 0. First, we are given that the particle starts from rest at t equal to 0. So at rest means it has something to do with velocity at t equal to 0. So let's see, what does that mean? So velocity at time t equal to 0 is equal to, plug t equal to 0 in the function that we have given. So it's v naught plus 0 plus 0. And we are given that it is at rest at that point, so that's equal to 0. So that implies that v naught in this particular situation is equal to 0. So our velocity as a function of time with this realization or with this deduction means first term is 0. So it is simply a naught t plus half b naught t squared. We have got rid of one of the parameters in that sense, or it doesn't contribute in this particular scenario. From this point, then you're given that determine the velocity of the particle when the instantaneous acceleration of the particle is 0. So next we have to find out at what time does the acceleration become 0. So we are to ask for what time. So acceleration a of t, when does that become 0? So there's a specific times when that is equal to 0. So we plug in our acceleration, correct? So this is a naught plus b naught times t is equal to 0. That implies there is a special time when that happens. So that's t is equal to minus a naught over b naught. So I solve for that. But it's not the time there that's being asked in the problem. At this particular time, that's a special time when the acceleration becomes 0. At that particular time, what is the velocity? That's the question being asked. So velocity at this particular time, so velocity is equal to a naught times t plus half b naught t squared. That's a general formula. But at this particular time, this becomes A naught times minus A naught over B naught plus half B naught times minus A naught over B naught square. The first term is negative, so it's square of A naught squared over B naught. And the second term as is it's not negative because negative squared is positive. There is a factor of half, and A naught squared still survives, and one of the b's cancel out, so that's B naught. These two are very similar terms. It's minus 1 plus half, so that's minus half A naught square over B naught. We're not given any numbers for A naught and B naught, so we cannot go any further. So that's what is expected. So this is the velocity. So this is the velocity at time t equal to minus A naught over B naught. So that's the time that was put in there. That's what the question is asking. Let me pause again. This is problem 4 in homework 2. And the problem says while standing on a 50-meter tall building. So let's say, let me draw the 50-meter tall building. That's your building. It's not really a vertical, so it's assumed to be vertical there. So that's ground. That's a 50-meter tall building. And you throw a stone vertically up while standing on the roof. Your height is negligible here. So you go up, all goes up, and then it comes down. And and it is right here on the edge of the building, so the ball doesn't come back and fall on the roof itself, but it goes all the way to the ground. The 2 points here are your the roof is the initial point, and right before it reaches the ground, it shouldn't be confused with the fact that after it reaches the ground, because after it reaches the ground, of course, it comes to rest eventually. But we're talking about right before it reaches the ground. That is where our equations are valid. After it touches the ground, our equations are not valid. So that's the final point. The final point is right before it reaches. There is a distance given to this, given to us, and that's 50 meters. We are also told that this velocity right at that point is 15 meters per second. So, so what are the quantities given? This is a kinematic motion of a falling, of an object falling under the under gravity. So there are 5 variables in this problem. So always it's delta x, that's x final minus x initial. There is time, we'll recognize each of this soon. There's an initial velocity, that's a final velocity, and that is acceleration. Since the stone is falling under gravity, the acceleration with which anything falls on the surface of the Earth, as far as you're close to the surface of Earth, then it is exactly minus 9.8 meters per second squared, 2 significant digits. If we talk about 3 significant digits, this changes 9.8. It is not really constant 9.8. Some places it is 9.76 or so, and in other places it could go as high as 9.84. But within 2 significant digits, it's always minus 9.8 at most of the places on Earth. And it is negative direction because everything, all the quantities we will try to select positive to be going in the upward direction. That's not really necessary, but it's less error prone in the early stages of these kind of calculations. So everything is positive in the upward direction, and otherwise it's negative. So delta x is x final minus x initial, and it is a displacement. Notice even though it goes up and then comes down, we don't worry about that going up and coming down. It negates itself. It is only the final minus initial, and final is lower and initial is higher. So it is going to be a negative number. So that's negative 50 meters. So we have two quantities given, and the third quantity is that the initial velocity is going upward, so it is plus 15 meters per second. And that collects our three quantities, and I mentioned earlier that, or in class, that out of these five variables, we are usually given three quantities, or it has to be three quantities given. What is being asked for in part A, how long does the stone take to reach the ground? So in part A, we are asking for delta t. And that makes this missing. That makes this the missing quantity for this process. And we also had the strategy that if one of the quantity is missing, look for the equation that does not have that missing that variable, because then we don't have to look for what we are actually something that is not given to us. But still, delta t should be there because we're solving for that. So the variable that we're solving for should be there in the equation. So the equation that we recognize out of the five equations is V initial delta t plus half a delta t squared. Once we know this, we simply substitute our numbers. So it's minus 50.0. That's equal to V initial is plus 15 times delta t we are looking for, and plus half times minus 9.8 delta t squared. Rewrite this all to the on the left hand side. 9.8 over 2 is minus 4.9. Bringing it to the left hand side, that's 4.9 delta t squared minus 15 delta t minus 50 is equal to 0. That's a quadratic equation. So that's delta t is equal to minus b, so that makes it a plus 15 plus or minus square root of minus 15 square, like that's b square, minus 4ac, so that's minus 4a is 4.9, oops, 4.9, this times 4.9, and you multiply it by minus 50. The negative, two negative signs makes it a positive. The negative 15 squared does not contribute a sign there, and is 2 times a, so a is 4.9. Let's first calculate the quantity, the discriminant of this equation. That's in the square root. So it's 15 square. I use using a calculator. And the next number is a positive quantity. So 4 into 4.9 into 50. That's 1205, and I take the square root. So let me write that down again. So it's square root of 1205 and divided by 9.8 in the denominator, right? So square root of 1205 is 34.7. So it's plus 15 plus or minus 34.7. I should have only two sig digits at the end because 9.8 has only two sig digits, the least number of significant digits is what you keep, and that's equal to the two solutions. So one is 15 plus 34.7 by 9.8. Now that's 5.1 seconds. That's plus 5.1 seconds. Or there's another solution which will be negative. So it's 15 minus 34.7 divided by 0.8. That's minus 2.0. Both answers are possible mathematically, but we know that we started at time we started the stone starts its journey at t equal to 0 from the top of the roof, so it has to reach the ground at a future point that is positive. So the solution is plus 5.1 seconds. So that's your answer. One could interpret what negative t.0 is if you had, since mathematics in this of this stone, all of these equations doesn't realize when it starts and end, it can actually project the stone actually backward in time, and wherever it starts from the ground, whoever threw this, if it were to be thrown at the ground, then that's what this minus 2.0 seconds mean. But in this problem, it's the first solution that is the answer. Let's come to part B of the problem. Part B, how long, how high above the building does the stone reach? This is now we are to change the problem in the sense the initial point is still the roof, but the final point now is the top of the trajectory. So that's your final point. It's no more the ground. So we just stop the problem right after the stone reaches the top. And again, we have five variables. So delta x, delta t is a new description, even though the stone is the same, the system is the same, but the initial and final points are different. It's still falling under gravity, so it's minus 9.8 meters per second squared. So that doesn't change. Initial velocity is still 15 meters per second in the upward direction. That's plus 15. What else is given to us? What are we asked to find? How high above the building does the stone reach? So that's delta x. We are asked to find delta x. Time is not given to us, and it seems like in the naively the final is also not given. But that's the concept that comes in here. How high above the building does the stone reach? And the highest point is velocity is 0. So that's a concept there. So it's not explicitly given, but we have to read out or we have to understand that that's the boundary condition given. Once we use that, there are 3 out of 5 variables known, and the missing variable is delta t. We look for the equation that does not involve delta t, and that equation is 2 times a times delta x is equal to v final square minus v initial square. Plug in the numbers. So that's 2 times minus 9.8 times delta x is equal to 0 square minus 15 square. Dropping the units for a moment for avoiding the clutter. So there's negative sign on both sides, so that doesn't contribute. So this is equal to uh, 15 square divided by 2 times 9.8. So that's 9, denominator is 19.6. Numerator is 225, so we have 11.5, but there are only 2 digits, so this is 11.5 meters, but we should round this off to 12 meters. Only 2 digits there, so it goes 12 meters above. So the height of the building was 50 meters. Relative to that, it further goes up 12 meters. Let me pause here before I proceed. Coming to problem 5 in homework 2, talks about a fish that is dropped by a pelican that is rising steadily at a speed of 4 meters per second. Rising steadily means that it is not accelerating. So as far as the pelican goes, so let me show the picture. So that's your pelican that's rising steadily at 4 meters per second. So pelican is, is moving with a uniform velocity, since it can provide, like everything tries to fall under gravity, but pelican has wings, so it can actually control its motion, and it is going at uniform velocity. Fish, on the other hand, cannot fly, so it just falls under gravity, and we know that anything falling under on the surface of Earth, close to the surface of Earth, it falls with uniform acceleration. That's the slight difference between, or the difference between the pelican and the fish. But both the pelican and the fish were going together up, because pelican was holding the fish. So both were going at 4 meters per second up. So fish was also going at 4 meters per second. But the fish is dropped. Even though it is dropped, it shouldn't be confused that the fish will immediately starts going up, because it has a velocity already, because it was moving with the pelican. It will keep going up for a moment. It will keep going up and then come down. Like all this happens along a straight line, and eventually it will reach the ground, which is actually not the ground, which is the water. Right. And we would like to know at what time after it is dropped does it reach the ground. So that's part A of the problem. Further, in that same time, in the time the fish dropped and reached the ground, pelican keeps going up. Right? Pelican keeps going up, and it reaches somewhere here. We would like to know how high as the pelican, how high above the water is the pelican. So we would like to calculate that height. First, let's calculate the time. Let's So the initial, we are talking about the fish now. So that's your initial point, and that's your final point. Like how much time does it take for the fish to reach the water? So delta x is given for us. It is 15 meters below, and the final point is below the initial point. So if we choose everything to be positive in the upward direction, so that's 15 meters below. So it's negative 15 meters. Time taken, that's what we are actually wanting to calculate, determine the time taken for the fish to reach the water. So that's a unknown quantity. V initial is plus 4.0 meters per second, because the pelican is steadily rising up, we are given. V final, when it reaches the water, or right before it reaches the water, we don't know that. So that's, in a sense, the missing variable, because one is unknown. And acceleration due to gravity is minus 9.8 meters per second square. Once we know the missing variable, we immediately know how to which equation it is. So that's the initial delta t plus half a delta t square. It was very similar to the earlier problem, except the numbers are different. So that's minus 15 is equal to V initial, so that's 4.0 delta t, and minus A is 9.8 divided by 2, there's a negative sign, that's minus 4.9 t square. So that's 4.9 t square minus 4.0 delta t. Oops, that's delta t. Delta t minus 15.0, that's equal to 0. What's the solution to this? So delta t is equal to plus 4.0 minus b plus or minus b square minus 4ac. So that's minus 4.0 square minus 4 times a is 4.9 like last time, and c is minus 15.0, and divided by 2 times 4.9. That's equal to plus 4.0 plus or minus the square root of that quantity is it's positive, so 4 into 4.9 into 15. That's the second term there, which is positive, plus 16. 4 into 4 is 16. So it's plus 16. And we want to take the square root of that. So it's square root of 310. 17.6. We need only 2 digits, but write the third significant digit in the intermediate steps. That's 9.8. Again, it is the future, and future time that is going to be relevant. The negative time should not is not what is asked for. So it's 4 plus 17.6 divided by 9.8. That's 2.2 seconds. It's plus 2.2 seconds. The second solution will be negative, so which is not relevant for this. Once we have the time t, in that same amount of time, the pelican is going to move upward from already 15 meters that it already has, because that's where it begins from. So what's the position of the pelican? So as far as the pelican goes, the position is delta x is equal to, already it has 15 meters, that's 15 meters, plus it's going with uniform velocity. The displacement in uniform velocity is whatever its velocity is times delta t. It doesn't matter initial or final because it's constant for uniform velocity, and time we say is 2.2 seconds. So so already starts from 15.0 meters. Velocity is 4.0. It keeps steadily going at 4 meters per second, and the time is 2.2 seconds. So that's 2.2 into 4. So that will be 8, I suppose. 8.8 plus 15, and that's 23.8, which is 24 meters to 2 digits. That's the height of the pelican above the water surface. Let me pause again. This is problem 6 in homework 2. Talks about a car. So let's say we have let's say a road, and there is traffic lights here. So let's say that's red or green, right? So it's traffic lights, red, yellow, green there, and we have a car starting from initial point A, and while it crosses point A, the driver notices that the light has turned red, but he or she is not able to press on the brakes right away because it takes some time to process the red light and for the brain to give the signal that we have to press on the brakes. And that usually could be anywhere between 0 to 1 seconds. It usually is a fraction of a second. And if you're not attentive, it could be a larger time too. So it is given that it's zero point 0.5 second, but in that moment it is going with uniform velocity. So in that time it reaches here, let's say point B, and in this segment of the motion, this is going with uniform velocity. So it steadily keeps going from that point on to point C somewhere. Let's say it doesn't have to be reaching exactly at the red light. It could be somewhere before, or it could be somewhere after. So then some arbitrary point C, that's where it comes and stops. But once the driver is hit on the brakes, it is actually decelerating. So that's uniform acceleration, or you can say uniform deceleration. So it's uniform acceleration. Acceleration here is a general term. Okay, so let's talk about motion from A to B. That's uniform motion. So delta x is simply v times delta t. That's the only equation for a uniform velocity. Velocity is given to be 10 meters per second. It's 10 meters per second times time. It is 0.5 seconds. That's the time for which or before which the brakes are not yet hit, and so it's going with the uniform velocity. So that's 10 over 2, so that's 5 meters, but that's 3 sig digits, so it's 5.00 meters. So that's the distance A from between A and B. That's the amount of distance it has traveled before the brakes are hit. After the brakes are hit, that's going from B to C, that is deceleration, and now that's uniform acceleration motion. So that's 6 variables: delta x, which is what we are interested in finding out; delta t, we don't know, we're not given the time; initial velocity is at point B, it is moving at the same velocity as point A because no acceleration has happened. So that's still 10.0 meters per second. And at point C, it comes to a rest. So V final is equal to 0. And acceleration is given to be, it decelerates at 8 meters per second square. That's minus 8.00 meters per second square. So we have 3 sig digits in all these numbers. So the answer should be given 3 sig digits. What are we looking for? How far? What is the stopping distance of the car as measured from the point where the driver first sees the light? So first let's get B and C. So that's what we are interested in, and that's a missing variable. If time is missing, the equation we would look for is 2 times A times delta x is equal to V final square minus V initial square. 2 times minus 8.00 times delta x, you can find out, is equal to 0 square minus 10.0 square. So delta x now, this is maybe differentiated from the earlier delta x. So this is from B to C, delta x BC if you want. It's subscript BC is 100 divided by 16, which is 6.2 6.25. And the earlier distance that we calculated, that was delta x AB. So what's the total distance that the car has moved since he or she saw the lights is delta XA plus delta XBC. That's 5.00 plus 6.25. All the numbers are the 3 sig digits. So this will be 5 plus 6, 11.25 meters, but it should be three sig digits, so it's 11.3 meters. That's the distance that's asked for. Let me pause again. This is problem 7 and homework 2. It is recording. I'm just confirming that. This problem 7 talks about a speeding car, uh, a speeder, uh, or a cop trying to catch up with a speeder. So let's represent the lanes on, let's say this is an interstate road, and these two lines represents two lanes on this road. And let's say one is covered by the speeder, and the second is by the police car or the cop. Car. Uh, the speeder is going with uniform velocity. That's given to us. It's going at constant speed of velocity. It's given in 80 miles per hour. That's 35.8 meters per second if you convert it into meters per second. And the cop, if he has to catch up, he has to accelerate because the cop is at rest to begin. So it's going at uniform acceleration. If a cop is at rest, he has to move. If she has to move, and it has to be accelerating for the. When does the motion analysis begin? Whenever the speeder crosses the cop. So cop was at rest here. V is equal to 0 for the cop, but V is equal to 35.8 for the speeder. So this is the speeder's velocity, but this is the initial velocity of the cop. And eventually, since the cop is accelerating, eventually the cop will, how much ever time it takes, since the speed keeps increasing for the cop, uh, he or she will actually cross the speeder at one point, and let's say that's the point where that happens. At that point, we have final velocity v final, and since it starts from rest, we have it growing quadratically in time. So as far as the speeder goes, it's going with the uniform velocity. So delta x for the speeder is the speeder's constant velocity times time. As time evolves, the position of the speeder changes. As far as cop goes, this is delta x cop c is equal to velocity, initial velocity of the cop, that's equal to 0 plus half at square. Acceleration is for the cop, and that's delta t square. As time evolves, the position of the cop changes. But right when they cross each other, both are the same. So that's the concept, that right when they're crossing, delta xc is equal to delta x. Or the position of the speeder and position of the cop is the same from the earlier point where they crossed. That means Vs times delta t is equal to half a times delta t square. One of the time cancels out, and we can solve for the time, which is what we're interested in. So it's Vs over a. That's equal to 2 times the velocity of the speeder, that's 35.8 meters per second, divided by the acceleration, which is 2.0 meters per second square. Right. So that's 70 point, so multiply by 2, so that's 71.6 divided by 2. So let me calculate that. That can be done in head. Calculating. And we do have 3 sig digits in all the, no, we have only two sig digits in 2.0, so we keep it only to 2 sig digits. So that's 36 seconds. But we can also, once we have the time, we can calculate how far the cop or the speed rest traveled since they crossed. So at that time, we can either ask what is the distance delta x cs, which is the same as delta x cop, is equal to, we can use either one of the formulas. So let's use the simpler one, Vs times delta t. So that's equal to 35.8 times 36 seconds. Because 2 cancels out. So into 36. That's 1288.8 meters. But again, we should keep only two sig digits. So we surround it off to 1,300 meters. And that's the distance the cop travels in that particular time. Let me pause this now. This is problem 8 in homework 2. We talk about a bridge. So this is the position in a bridge. It is coming out of the boat, so you could be standing here and looking down uh, at water flowing down here. And let's say that's the point right underneath the bridge. There is a boat that's traveling towards the bridge, and let's say that's the velocity of the boat, and that's going with uniform velocity, so it keeps going at the same speed. And this distance is given to be 10 meters to 3 digits. This height, this is not a scale. If this is 10, this also seems like it is 10, but it is given that this is 50 meters. So it's 50 meters. Clearly, the y scale is not the same as x scale, the way I've shown. A key is dropped, and while it drops, it is accelerating. And it is released right when it is 10 meters, the boat is 10 meters away. And it turns out that the key exactly falls inside the boat. So that means to say that the amount of time the boat takes to go 10 meters is the same as the amount of time the key falls from the vertical height. So boat is going with the uniform velocities. That's identification. And as far as the key goes, that's uniform acceleration. Further, let's as far as the distance goes, this is, let's say, delta y, right? That's delta y, that's delta x, which is the key falls vertically down and it's released from rest. So that's half at square, or let's say half a delta t square. And acceleration is minus 9.8, but the positive distance will be just 9.8, or you can say delta y also will be negative. As far as the boat goes, it travels a distance delta x. It's going with uniform velocity. So delta x is equal to velocity of the boat times delta t. And of course, delta t is exactly the same for both. Right. So let's calculate delta t from one. This is a coupled problem. We put it into the other. So the key information is given to us to be, so that's minus 50 meters. That's equal to half times minus 9.8 times delta t squared. That allows us to calculate delta t is square root of 50 into 2 divided by 9.8. And that's 3.2 seconds to 2 seconds. Once we have the time, we can substitute this in the second equation. Delta x now is 10 meters. Velocity of the boat is what we are interested in, and the time is 3.2 seconds. So velocity of the boat is 10 divided by 3.2, and that's 3.125, so it's 3.1 meters per second. So that's the velocity of the boat, which can be determined in this simplistic way, which is reasonably precise if we can actually calculate the time and distances reasonably precisely. And I'll finish this recording at this point. Stop recording.